Hello, I'm Paul Tromp. I'm a certified petroleum geologist and one of the founders and still a shareholder in the Discovery Coal Bed Methane Project. And I'd like to give you an overview. First of all, what is coal bed methane? The layout of the production license, our exploration results, a global comparison with other coal bed methane projects, and what we've done in terms of production testing to date. So, what is coal bed methane, or what the Australians call coal seam gas? It's simply another form of natural gas. It's more concentrated in methane coming out of the coal and only has traces of propane butane, unlike other forms of natural gas, but it can be put in pipelines and used just like any other natural gas for power generation, vehicle fuel, and petrochemicals. And the very formation of coal, in this case, Permian aged, pre dinosaur, about 180 million year old peat forests, as the South Pole was over South Africa at the time. So the conditions were something like you find in modern day Canada, and very prolific formation of peats, which, when the basin subsided and other sediments were laid down, the climate became drier. The coal, peat was compressed into coal, which by definition creates methane. It also creates shrinkage in the coal, creating permeability cracks, which are called cleat. Unlike conventional gas deposits, which are very small, bullseye type targets, nice to find, but difficult to find, once you establish a coal bed methane basin with good gas content, and the appropriate depths of about 200 to 1200 meters, you have what's called a resource play, whereby you can drill wells, thousands of wells in many cases, with very low risk. They will vary from well to well. The volume will be moderate, but they're very shallow wells by oil and gas standards and will be very inexpensive to drill compared with the conventional gas deposits. The way the wells are constructed is a hole is drilled down to the top of the coal seams and steel casing is cemented. The last thing we want to do is get water out of something that doesn't have gas, and we won't be doing any fracking. We then drill out through the coals, below the coals, put in a pumping system to lower the water level, lower the static water level in the coal, which will start the gas releasing. In some cases, the gas starts coming out straight away. In some cases, it can take weeks or even months, depending on how much water needs to be removed. And ideally, this is a team sport with numerous wells working together like a football team, helping to get that water level and water pressure down so that the gas can come out. And we think that we're probably looking at between 4 and 9 wells per square kilometer to efficiently drain this without any fracking. This is a little bit of an old map of world coal bed methane, but it is something that is spread all over the world. And as of 2016, estimated over 100,000 coal bed methane wells around the world. And it certainly registers as one of the unconventional gas forms, like shale gas, tight gas sands, and CBM is among them. And in fact, the Zimbabwe project has a lot of very dirty coal, which is not mineable and would actually qualify as shale gas. So technically, it's a CBM slash shale gas project. And this was the US CBM production. It was overshadowed by shale gas in the last 15 or so years, and so has been in decline. And looking at world CBM production, China was a little bit off to a slow start, but producing a lot of coal bed methane, and the various other countries. Canada has passed its peak, but continues to produce from CBM wells. CBM started in two basins in the States, San Juan and Black Warrior basins, back in the late 70s, when coals were realized to be a gas reservoir. I'd like to talk a little bit about a basin that I worked in for 10 or 12 years, from the late 90s on through to about 2010. And during that time, over 33,000 wells, that's just in a 12-year period, were drilled. But it's a fairly good analogy for Zimbabwe. Zimbabwe should be even better. Basically, the Powder River Coal Basin is now supplying more than half of all the U.S. coal because it's a low sulfur coal compared with the eastern coals. And the picture on the left is one of the single seams, 100 feet or 30 meters thick. And I'm going to use that as a scale compared with what we have in Zimbabwe in a later slide. But yeah, that's a lot of coal. And this is a map I generated back in 2010. At that point in time, there were over 33,000 coal bed methane wells. Over 4 trillion cubic feet of gas had been produced, and some of the wells that weren't connected yet are also interspersed through this area. But a lot of drilling activity. There were at times over 100 different operators drilling and producing coal bed methane. So keeping the Powder River coal bed fairway in mind and putting it to the same scale on a map of southern Africa, you can see that we're dealing with, in the case of the Discovery Project, a similar basin size. And above and beyond that, we also have very thick coals, moderate gas content like the Powder, actually better than the Powder River Basin overall, good inherent permeability, and this is why we haven't seen a need to do any fracking to get a commercial rate. And the reason for that is, in case of both basins, there's not been a lateral squeezing, mountain building, pushing the coal cleat, the coal cracks closed. So the inherent shrinkage cracks in the coal are still there, giving you good inherent permeability. Things that are better in the Discovery Zimbabwe Basin, we're dealing with older, higher ranked coals. They're about 100 million years older. The coals in the Powder River Basin are post-dinosaur. Ours are pre-dinosaur. And so that extra time of geothermal heating in the ground has generated more gas than the Powder River Basin. And in some cases, we at coals at 1,000 meters or so have very high gas content, much like some of the other basins in the U.S. and far in excess of what you find in the Powder River Basin. And interspersed with the coals are thick coaly mudstones. Because this was a cold climate when the coals were being deposited with freeze-thaw cycles, winter and summer, you have a lot of sedimentary material washed into the coal seam. So a lot of the coal measures are not mineable, but they certainly have gas in them. And Zimbabwe has a desperate need for energy to replace coal. They have endured frequent power cuts over the last decade or more, and petrochemical generation from electrolysis has been cut off. So there's a lot of fertilizer import that used to be produced within the country. And lastly, I've also worked on projects in Botswana and Zambia looking for CBM, and the gas content in those countries is just too low to be commercial. So the point here is that Zimbabwe could not only be its own market for gas, but there could easily be export to neighboring countries. This map shows where the discovery license is. It's about 1,100 square kilometers overall. It is a production license, and it's situated sort of midway between Bulawayo, world famous Victoria Falls, and the capital city of Harare. And of note are two 330 kilovolt power lines, which connect the Wangi power station, where most coal mining is conducted, to the regional grid, the Southern African Power Pool, SAPP. So currently, power can flow between about a dozen countries in Southern Africa. Those lines are only halfway full of power. So power generated from discovery could go either way to connectors to the Southern African Power Pool and go to any of the neighboring countries if there's excess power to what Zimbabwe would consume. Another positive about our license area is there is a medium voltage 33 kilovolt line which runs right past where our test wells are located. And that gives an opportunity for small scale early days power generation from the license. Our exploration activities included drilling 5 areas with core drilling, same kind of thing you'd do for coal exploration or other mining activities. And when the coal samples are removed, they are first, right when they come up out of the hole, about 10 or 15 minutes after they've been drilled, we put soapy water across them to give a visual indication of gas coming out of those coals or coaly mudstones. They're then measured up, described, and put in desorption canisters to measure the gas. And they're put into desorption canisters to be measured for the gas content over a period of about 3 months, kept at reservoir temperature to replicate the conditions from which the coal has come. And the results are, just to compare them to other North American plays, a common unit used in the gas industry is billion cubic feet per square mile. And that gives you a way of comparing various projects, in this case, Canada, the United States, and one listed for China. And you can see that the range goes up to about 30 BCF per square mile. In our western area, it's a bit shallower than to the east. And the numbers there, the figures there, 21, 12.5 BCF, are well within the range of comparable projects, commercial projects in North America. What we found in the area where we ended up putting in our test wells is we're looking at about 89 BCF per square mile. And that's 3 times the best of these listed basins for CBM. We also determined that in the wireline logs and in the visual wall coring, that there could be as much as 13 BCF per square mile in the sandstones, much shallower than the coal. We have yet to test those, so that's just some possible addition, which would come out faster than the gas from the coal. This map then divides the areas into what this well defined as being sort of in the center of an area, a deep area. So we're using that as an example of what is shown at the top of the screen for the average for the area, about 150 meters of gas-bearing coal and coaly mudstone with an average density, a gas content. At any rate, that gives you a resource, a gas in place of 17.9 TCF. Huge amount of gas. If we assume a 65% recovery factor for the gas in the ground, that then gives us 11.7 TCF of what would be an estimated reserve, what we could expect to come out of the ground. And given that these wells will probably have a life of 20 or 30 years, if we use a long run marginal price of $6 per gigajoule over the life of the wells, we're looking at a gross value of that gas of about 70 billion US dollars. And that doesn't include any potential from the sandstones. The medium depth area outlined in blue is based upon a well that sits sort of in the middle of that depth zone. And long story short, that could give us another 12.8 billion US dollars of gross gas value. And this gives you a visual of what we're dealing with. These are geophysical wireline logs, tools that are put down the hole after drilling. And the takeaway from here is that everything that is shaded in pink had gas and was tested in nearby core holes. These are actually test production wells. And you can see it's well over 100 meters. If we look back at that picture of the coal seam from the Powder River Basin, we can see that it's dwarfed by the shear thickness, albeit thin zones, but massively adding up to over 150 meters in this area. These wells are only about 200 meters apart for our first test field. This is where it gets really interesting to compare with other basins in North America, where there's sort of a basin low and a basin high for BCF per square mile. And even our low end in the Discovery Project is comparable to these other CBM commercially producing basins. Our high area is just off the charts by comparison, with 89, not including the sandy sandstone gas that we might get. If we take those same values onto another chart in a logarithmic scale, it's interesting to note that the average daily production per well for these other basins, compared with the gas in place, then look at Zimbabwe Discovery, where we have a much higher gas in place, 89 BCF per square mile. So it's very reasonable, very conservative that we look at averaging about 300 MCF or 300 gigajoules per well per day. And anything above that will certainly be cream. It expected that it's probably going to be higher than that, but we're not going to uh, predict what we're going to get. Production testing. At the time when we drilled the wells, there were very few operators in the region that had the capability, the compressors and booster to drill with air to 800 plus meters. So our only choice was to drill with mud, which we knew was less than ideal for coal bed methane wells because mud drilling using water with drilling mud does tend to plug off the permeability, the cracks in the coal. And we did find that to be the case, but we still got commercial results despite that. This is a satellite view of the three wells. They're about 200 meters apart. We have evaporation ponds located to evaporate the produced water. We have a camp set up there as well. And all three wells did produce gas. Only one of them was commercial in nature because of the mud damage. The DI3 well, over about a 2-week period, was producing uh, moderate amounts of water and very little gas. And then one evening, in minutes, something broke loose, kicked out the mud plugging from some of the coals, and it started gaining more and more gas flow. And at the end of about 2 weeks, we found that the gas flow rate was up over 130 MCF per day, or gigajoules per day, and still rising. And it was the one well doing this all on its own in a team sport. So very, very positive results. And as we said, we expect it to be more like, stabilize at more like 300 MCF a day, perhaps more. And just to do a what if we look at this deepest of the deep areas close to the power lines, we estimate that at 9 wells per square kilometer, we could drill 2,000 wells in here. And over the course of the life of those wells, we would be producing an estimated 7.4 TCF with a lot more room to roam. So I hope you can be as excited about this project as we are, and look forward to answering questions as they come up.